The NASA ESA Hubble Space Telescope has discovered an extrasolar planet, for the first time using direct visible light imaging. The strange world is far flung from its parent star, is surrounded by a colossal belt of gas and dust, and may even have rings more impressive than Saturn's.
This is the Hubblecast, news and images from the NASA ESA Hubble Space Telescope. Travelling through time and space with our host, Dr. J, aka Dr. Joe Liske.
Hello and welcome to another episode of the Hubblecast. Our favorite orbiting observatory has been busy helping astronomers to study extrasolar planets, those enigmatic worlds orbiting stars other than our Sun. And what do you know? Hubble has done it again. It has delivered yet another stunning breakthrough when it turned its gaze on the star Fomalhaut.
Fomalhaut is visible from the southern hemisphere and is one of the brightest stars in our night sky. Lying around 25 light-years distant, it's also relatively close. Fomalhaut is much hotter than our Sun and 15 times as bright. It's blazing through hydrogen at such a furious rate that it will burn out in only 1 billion years, 10% the lifespan of our star. But perhaps its most interesting feature is the large disk of gas that surrounds it, looking like a lifebelt. It's this ring which first sparked the attention of astronomers. It isn't centered on Fomalhaut quite as predicted, hinting that the gravity of another body, perhaps a planet, is pulling it out of shape.
And so Hubble was called upon to solve the mystery of the misshapen disk. And, lo and behold, the image produced by Hubble actually does show a planet. It orbits Fomalhaut at an enormous distance, about 10 times the distance between Saturn and the Sun. In honor of its parent star, astronomers have given this planet the extremely catchy and very imaginative name Fomalhaut b.
Planets around other stars have been detected before, but usually indirectly by looking for clues, like the wobbling motion of a star as a planet orbits it, or a star getting dimmer as a planet passes in front of it. This time, Hubble has given us a rare direct image of an extrasolar planet, and what's more, the first invisible light, the type our eyes naturally see.
Amazingly, Hubble has managed to take a snapshot of this planet not just once, but twice, with almost 2 years in between. Being able to actually see the same dot of light moving around the central star is a very clear sign that this object really is in orbit, and that it's not just something that happens to lie along the line of sight. Now, astronomers have calculated that it takes this planet about 872 Earth years to complete one orbit. Now, taking an image of an extrasolar planet is a very tricky business. Fomalhaut is one of the brightest stars in the night sky. By comparison, the planet is just a very tiny dot of light. Now, being able to see that light was only made possible once most of the light from the star was blocked using an instrument called a coronagraph.
So Hubble managed to peer through the glare and view the planet directly. Then clues were gathered to paint a picture of this exotic world. The shape of the disk hints that the planet is at most 3 times the mass of Jupiter. And the observations show that Fomalhaut b is much brighter than expected for an object of its size. It could have an enormous ring system, much larger than Saturn's, reflecting starlight in all directions. One day the material in these rings may even coalesce to form moons.
Unfortunately, we won't be visiting this planet anytime soon. Although it's actually pretty close to us in a cosmic sense, a spaceship would still take thousands of years to get there. So it's lucky that we have Hubble to give us the next best thing: breathtaking images and incredible science. This is Dr. J signing off for the Hubblecast. Once again, nature has surprised us beyond our wildest imagination.
This is the Hubblecast, news and images from the NASA ESA Hubble Space Telescope. Travelling through time and space with our host, Dr. J, aka Dr. Joe Liske.
Hello and welcome to this fourth special episode of the Hubblecast, celebrating the International Year of Astronomy in 2009. In the last episode, we saw how the advance of technology through the 1970s and 80s revolutionized astronomy. Today, we'll discuss how astronomers detected and measured light over the years, from hand drawings to electronic detectors. 400 years ago, when Galileo Galilei wanted to show others what he saw through his telescope, he had to make drawings. The pockmarked face of the moon, the dance of the Jovian satellites, sunspots, or the stars in Orion. He took his drawings and published them in a small book, The Starry Messenger. That was the only way he could share his discoveries with others. For well over 2 centuries, astronomers also had to be artists. Peering through their eyepieces, they made detailed drawings of what they saw. The stark landscape of the moon, a storm in the atmosphere of Jupiter, the subtle veil of gas in a distant nebulae. And sometimes they overinterpreted what they saw. Dark linear features on the surface of Mars were thought to be canals suggesting civilized life on the surface of the red planet. We now know that the canals were an optical illusion. What astronomers really needed was an objective way to record the light collected by their telescopes, without the information first having to pass through their brains and their drawing pens. Photography came to the rescue. The first daguerreotype of the moon. It was made in 1840 by Henry Draper. Photography was less than 15 years old, but astronomers had already seized on its revolutionary possibilities. So how did photography work? Well, the sensitive emulsion of the photographic plate contained small grains of silver halide. Expose them to light and they turned dark. So the result was a negative image of the sky, with dark stars on a light background. But the real bonus was that the photographic plate can be exposed for hours on end. When you take in the night sky with your own eyes, once they're dark adapted, you don't see more and more stars just by looking longer. But with a photographic plate, you can do just that. You can collect and add up the light over hours on end. So a longer exposure reveals more and more stars. And more, and more, and then some. In the 1950s, the Schmidt telescope at the Palomar Observatory was used to photograph the entire northern sky. Almost 2,000 photographic plates, each exposed for nearly an hour. A treasure trove of discovery. Photography had turned observational astronomy into a true science. Objective, measurable, and reproducible. But silver was slow. You had to be patient.
The digital revolution changed all that. Silicon replaced silver, pixels replaced grains. Even in consumer cameras, we no longer use photographic film. Instead, images are recorded on a light-sensitive chip, a charge-coupled device, or CCD for short. Professional CCDs are extremely efficient. And to make them even more sensitive, they are cooled down to well below freezing using liquid nitrogen. Almost every photon is registered. As a result, exposure times can be much shorter. What the Palomar Observatory Sky Survey achieved in an hour, a CCD can now do in a few short minutes, using a smaller telescope. The silicon revolution is far from over. Astronomers have built huge CCD cameras with hundreds of millions of pixels. And there's more to come.
The big advantage of digital images is that they're, well, digital. They're all set and ready to be worked on with computers. Astronomers use specialized software to process their observations of the sky. Stretching, or contrast enhancing, reveals